Good morning. I'm Richard Jaenicke from Mercury Systems, and I'm here to talk to you today about trusted computing, and more specifically, how we merge the trusted manufacturing, safety, and security together to get a full solution. You know, and those components really do interplay. You can't really have safety without security. If somebody can hack into your system, it's probably not going to be safe. And you can't. And it really doesn't make much sense to secure something that you don't trust in the beginning, because otherwise you're securing something that has lots of backdoors and Trojan horses, and that doesn't get you anywhere. So there's an interplay here. But what do we really mean by trust? You know, trust is at lots of different levels. You know, if you look at the person sitting next to you today, do you trust them? And I've known a lot of you guys for a long time, and I can say with a few notable exceptions, and I'm not looking at anybody in particular, that, you know, it's a pretty trustworthy bunch here. But look again, and if we get more specific and say, would you trust that person to design and manufacture a computer for you in such a way that it would perform, it would be reliable, it wouldn't have any backdoors or counterfeit parts in it? You know, might have to think twice. Would you trust them to operate it safely? Would you trust them to secure it, not click on any funny emails or weird links or visit any nefarious websites? No, I don't know. Now you have to think twice. So what does it really mean? If we think about the goals of a trusted system, you can break it down into 5 general areas. One is the functionality. You want to make sure that it has the performance, it does what it says it's going to do, and it does it safely, especially if you have some mission-critical application. You want to make sure that that system is available, that it's working, that it keeps working, that it is reliable over time. You want to make sure that it has integrity, that only the things that it's supposed to do are what it's doing. It doesn't have any Trojans or backdoors or any other extra features. You want to make sure that it can protect your IP, that it has confidentiality, that it protects your algorithms and your data. And you want to make sure that it only allows authorized users. That's both initially to access the system and also after they access it, that they can't escalate their privileges to be able to do something more than what it was designed to do. So how do we get there? What are the processes for doing it? Well, first you have to design and manufacture a system that you trust, and then you have to protect that system to make sure that it stays trusted and it stays trustworthy. And in the design and manufacturing, you're worrying about things like quality, designing in for reliability, designing for safety. And those are things that you can't add later. You have to do it during the design phase and continue it through the manufacturing phase, including making sure it has the integrity. Once you deploy the system, you need to protect it against remote threats through cybersecurity, and you need to protect it against local threats, the physical security that prevents reverse engineering. If you look at some of the images here, you'll notice that actually those are all pictures of an EP3. You know, from the wireframe of seeing what goes inside of it to flying around, and then that last picture is on the ground. And not a place it was really supposed to be. If you look carefully, you can see that the nose cone is damaged. This is the plane that was forced to land on an island in China. And you can imagine that that's pretty much the definition of where you want to have some of the best protections against reverse engineering and data extraction. So if we look more closely at the design and manufacturing, what are we trying to prevent? We're trying to prevent flaws in the functionality, flaws in the performance, any flaws that might make it operate in an unsafe manner, which is non-deterministic. Any flaws that include malicious alteration, those backdoors and Trojan horses I mentioned. And you want to make sure that the design IP isn't stolen. And you have to worry about these things through all the phases, from design through manufacturing, because all of them are vulnerable. And a big part, maybe the weakest link in all of this, is often the supply chain. So not very many companies make their own PCBs. So you have at least one supplier, and your chips are coming from somewhere. There's more suppliers. So, what do you do? Well, you really have to make sure that a lot of this trust gets pushed down into your supply chain. And, an example of how the supply chain is the weakest link is some of the news that came out in October, when we all found out that an Australian defense contractor was hacked. And this was a small company that had permission and had authorization to have secret data on the F-35, the P-8, the C-130, and even the smart munitions JDAM. And a lot of that design data was stolen. We can only imagine where it ended up. Not a good day for trusted systems. So when you're looking at a company, and you're trying to figure out, are they doing a good job at protecting and trusting, protected your systems while they're designing and manufacturing, how do you figure that out? Well, you can look to see if they have AS9100. That means that they have good design processes, that they're testing to their processes, and hopefully finding performance and functionality flaws. You're all familiar with VITA-47 here, that can help test reliability. Yesterday we heard about the avionics safety tests, certifications for DO-254 and 178. There's not really a good standard for preventing malicious alteration. And but a basic thing you can do is make sure there's no foreign influence, that you have US persons on US soil and a US-owned company making those products for you. For stolen data, there's actually new regulations in the DFARS that at the beginning of this year, all defense contractors have to follow this new procedure that includes NIST 800-171 that tells you how to secure your facility. You have to have your design information on a different network than your business systems. You have to have specific user access levels. You can't give everybody super user. There's a lot of other points in a checklist that you need to go through, and all the defense contractors had to go through that and be compliant, or at least show how they're going to be compliant shortly. Then you have protecting the data when it's deployed. There's standards that have been around for a while, like FIPS 140-2. And these are all really pretty much the first level, the entry level. And what if you want to have a company that does better than just okay? Well, for things like VITA-47, hey, there's a number of thermal cycles in that standard. You can always do more. You could double that. For the safety certifications, there's multiple levels. From level E is the easiest, level A is the strictest. Maybe you go for companies that know how to do level A. And if they have their designers or the people who know how to do the safety certifications, and you have in-house safety experts, that can be very reassuring. For the malicious alteration, there is something you can do. You can actually go to the Defense Microelectronics activity. They have a certification program where they go and certify trusted manufacturing and trusted design sites. And their list is there. And you can go and pick out companies on that list for trusted suppliers. From a security standpoint, beyond the DFARS, there is the Defense Security Service. They do audits. You can go to a company that gets this audit, and you can see what level they passed. The highest rating they give is superior, so pick out a company that gets a superior rating. And for companies that get superior ratings over and over again, they actually give them an award. It's called the James Cogswell Award. And only in less than 0.5% of all companies that get audited get that award. So that's a pretty good place to go. For your deployed data, there's the NSA has a program where if you don't want to go for the whole shebang, the type 1, I think is called, it's very expensive, very long to get. They do have a newish program called Commercial Solutions for Classified, CFSC. You've probably heard of it. And there they cover lots of different technologies, but they have one for storage. And you can go and look to see if your storage supplier has a CFSC rating. It's a tough rating to get, and right now there's only one company that has that CFSC actually pass the rating and not just trying or in process. So what about the other side? What about protecting the system once it's deployed? Well, there's the cyber side, and what we're talking about there is disabling or denying access to your functionality. They could steal the data remotely. They could even take control. You imagine taking control of a UAV or even worse, maybe a missile. Then there's the reverse engineering, the physical protection. They can steal the data there, X-rays or whatever side channel analysis, taking it apart, looking inside. If they can get it to work, they could try and redeploy it for their own use. They could even try and copy it. Can they get enough of the algorithms, enough of how to build this to clone it and build more of them and put it to their own use? These are all things that you really don't want to happen. So how do you protect against that? Well, there are some commercial technologies. Yesterday we heard a great talk from Concurrent that talked about what Intel's doing. Xilinx also has some really good ones. These are examples of the best of breed. On the Intel side, we have protected boot and boot guard, trusted execution for a software root of trust. If you want a hardware root of trust, there's the enhanced privacy ID. You have platform trust technology, and then there's software guard extensions that provide enclaves or containers to help hold your sensitive data. That's a lot of stuff. Look, a couple of these talk about trust. You say, well, I must be covered. Well, I don't know. Why do I need more than one thing that says trust? Isn't there one? Shouldn't there just be one that covers all the trust? Well, no, you have these three. Well, is 3 enough? Well, no, not really. There's still holes there. They could probably use 3 or 4 more, too. And the way that we know that is because we've all seen the news about different hacks and different vulnerabilities. The latest ones, Meltdown and Spectre, just came out, and that's not just Intel. That's every processor with branch prediction and speculative execution. The sad thing is that the media went crazy over this one when this is probably the least important one, because this is just looking at things, it's not altering it, and in order to look at the secrets, you had to have some other way into the system. And those other ways into the system were in the previously reported flaws, like the one in the middle, where Intel talks about a security flaw in their management engine, their server platform services, and their trusted execution engine. The thing that most companies in this room depend upon to protect them, this is where the flaw was. And it affects 3 generations of products and 8 generations of 8 families of products in 3 generations. So what do we do? Can any of the technology really protect us from this? So this is where Mercury specializes. That we really build around all of the security engineering. We've been acquiring companies and technologies and growing stuff ourselves for many years now. We have 30 people dedicated to working on this at the top echelons of government programs. Some of the IP that we have that can be applied is we can prevent unauthorized debugging. So that's going through the debug ports is a common attack vector. We can ensure clock integrity because changing the clocks around, you can see what happens and how it changes the performance and understand and get secrets from that. We ensure that you can boot securely. So it's a lot more than the boot guard. that you can get from a basic Intel or Xilinx. We can respond and respond and take countermeasures to unauthorized attempts, prevent reverse engineering, and help localize access through secure hypervisors. And this software has been tested and has been shown to be resilient to all of those attacks we saw in the previous slide. So in all of these cases, whether it's the management engine, the trusted execution engine, or even the Meltdown and Spectre, all of these are prevented by Mercury's built secure technology. And that technology started in VPX. VPX is a perfect place to deploy this technology, especially with the covers. It helps prevent reverse engineering. It's a good starting point. We've carried that through to advanced TCA into our ATX servers. So it's really a technology that expands across all of the different platforms. And it's one investment that we keep on making, and it's available for multiple missions. So trust, trusted design, trusted manufacturing, safety, making sure that it operates in a manner that you want it to, and security, protecting it throughout its mission and its life cycle. That's what trusted computing is about. Thank you.